Hello friends, welcome to my lecture on existence and uniqueness of solutions. First we shall consider a Cauchy linear partial differential equation of first order. Let us consider the equation as Px by z into the partial derivative of z with respect to x plus Qx by z, the partial derivative of z with respect to y equal to Rx by z. You can see that it is a Cauchy linear PDE of first order. Now we shall be discussing the method for solving the Cauchy problem for this Cauchy linear PDE. A Cauchy problem is what? A Cauchy problem in mathematics asks for the solution of a partial differential equation that satisfies certain conditions that are given on a hypersurface of the domain. A Cauchy problem can be an initial value problem or boundary value problem, or it can be neither of them. It is named after Augustin Louis Cauchy. The Cauchy-Kowalewski theorem says that the Cauchy problems have unique solutions under certain conditions. Let us discuss the theorem which gives the conditions under which a unique solution for the initial value problem for the first order Cauchy linear PDE given by equation 1 can be obtained. So let us discuss the theorem. It says that let Px by z, Qx by z and Rx by z in the equation 1 have continuous partial derivatives with respect to x, y and z, and let us assume that the initial curve which we denote by C be described as x equal to xs, y equal to y(s) and z equal to zxs by s. The initial curve C we assume that has a continuous tangent vector, and Js which is given by dy by ds into P minus dx by ds into Q xs by s zs is not equal to 0 on the curve C, then we can find a unique solution z equal to zx by defined in some neighborhood of the curve C which satisfies the equation 1 and the initial condition zxs by s equal to zs. So let us discuss the proof of this theorem. From the existence and uniqueness theorem of the ordinary differential equations, we have already discussed that the existence and uniqueness theory of ordinary differential equations, the characteristic system dx by dt equal to pxt yt zt, dy by dt equal to qxt yt zt and dz by dt equal to rxt yt zt with initial conditions at t equal to 0. At t equal to 0 the initial conditions are x equal to xs, y equal to ys and z equal to zs, possesses a unique solution of the form x equal to xst, y equal to yst and z equal to zst with continuous derivatives in s and t, and at t equal to 0 x is equal to xs, y becomes ys and z is equal to zs. The Jacobian of the transformation x equal to xst, y equal to yst at t equal to 0 is given by js at t equal to 0 which is equal to js, that is partial derivative of x with respect to s, partial derivative of x with respect to t, then partial derivative of y with respect to s and then partial derivative of y with respect to t. Now this is equal to partial derivative of y with respect to t into p minus partial derivative of x with respect to t into q, and we have assumed that js is not equal to 0. Js is not equal to 0 on C. So in view of our assumption, this is not equal to, this Jacobian does not vanish, and we have also assumed that C has a continuous tangent vector. So by the continuity hypothesis, j is not equal to 0, this j is not equal to 0 in some neighborhood of the curve C. Now let us apply the implicit function theorem, and when we apply the implicit function theorem, it follows that s and t can be solved as functions of x and y near C. Okay. So z as t is now z of x s y, z of s x y and t x y. S and t are now functions of x and y because that follows from the implicit function theorem. So z is also a function of x and y, z as t becomes a function of x and y. So this is a solution of 1. Now this z as t equal to z x y is a solution of 1 because r is equal to dz by dt from the characteristic system. From the characteristic system, r is equal to dz by dt, and dz by dt now can be written as dz by dx into dx by dt, because z is a function of x and y. So, dz by dx into dx by dt plus dz by dy into dy by dt, and from the characteristic system we know that dx by dt is equal to p and dy by dt is equal to q. So, p into dz by dx plus q into dz by dy. Okay. They should be actually the partial derivatives. We should be writing like this. This should be replaced by this, and then this should be equal to dx by dt is p. So, p derivative of z, partial derivative of z with respect to x, plus q times partial derivative of z with respect to y. Okay. So, when z as t is expressed as a function of x and y, okay, we find that it is a solution of 1, because r is equal to, when we find dz by dt, it turns out that it is equal to p partial derivative of z with respect to x plus q partial derivative of z with respect to y, which is equal to r. So, r is equal to this, and therefore, z is a solution of, z is equal to zxy is a solution of the given Cauchy linear partial differential equation of first order. Now, let us look at the unicity of this solution. The solution is unique, because by the uniqueness theorem for the initial value problem for the characteristic system 3, for this system, okay, the uniqueness follows because any two integral surfaces that contain the same initial curve coincide along all the characteristic curves which pass through the initial curve C. So, this is how we prove the existence and uniqueness of the solution of Cauchy linear PD. Now, using the Cauchy so we have discussed the method for solving the Cauchy problem for this Cauchy linear PD. Now, let us apply this result. So, let us consider the initial value problem, Zp plus q into q equal to 0, and where Zx0 is given equal to, so initial condition is given, Zx0 is equal to fx, which where fx is a smooth function. Now, what we do, so here when we compare this with the given form 1, with this given form 1, then what do we notice? Let us write the values of p, q and r. So, p is equal to z, q x by z is equal to 1, and r x by z is equal to 0. What we do is, to solve this initial value problem, let us first parameterize the curve C. Okay. So, let us first parameterize the initial curve. So, we parameterize the initial curve C by taking x equal to so let us take x equal to s, y equal to 0, then z is equal to and z equal to fs. Okay. Now, the characteristic equations are dx by dt is equal to p, so we get z, dy by dt is equal to q, so we get 1, dz by dt is equal to r, so we get 0. Okay. now what do we get? Dx by dt is equal to z. So this gives you d square x by dt square. We have to solve this characteristic equation. This so ds square x by dt square is equal to dz by dt, and dz by dt is equal to 0. So what do we get? D square x by dt square is equal to 0. X is a function of s and t. So when we integrate d square x by dt square twice with respect to t, what do we get? If you integrate it once, we get x is equal to some dx by dt equal to c1s. Okay, we are integrating with respect to t, keeping s as a fixed quantity. So dx by dt is equal to c1s, and when we integrate it once more, we get xst is equal to c1s into t plus c2s. Okay. Now we are given that at t is equal to 0, at t is equal to 0, x is equal to s. Okay. So what do we do? So at t is equal to 0, we are given x is equal to s, and when we put t equal to 0 in this, x s t becomes s. So what do we get? C2s is equal to s. Okay. So we get x s t is equal to c1s plus s. Okay. And when we differentiate it, dx by dt is equal to what we get? C1s into t, sorry, C1s into t plus C2s. C2s is equal to s, because at t is equal to 0, x s t is equal to s, and then dx by dt is equal to C1s from here. So what do we get? At dx by dt is equal to z. So z is equal to C1s. Okay, we are given dx by dt is equal to z. So this is we get xst. xst is equal to c1s. Oh, xst is equal to c1s is equal to z. So z into t plus s. This is xst, and by dy by dt is equal to 1 gives you by is equal to t plus some constant c3s. Now at t is equal to 0, by is equal to 0. So what do we get? 0 is equal to 0 plus c3s. So c3s is equal to 0 gives you by equal to t. Okay. So we have xst is equal to zt plus s, by equal to t, and dz by dt equal to 0 gives you z is equal to c4s. Now at t equal to 0, z is equal to fs. So what do we get? Fs is equal to c4s. So we get z equal to fs. Okay. So we have solved this system of characteristic system. We have got x is equal to zt plus s, by equal to t, z equal to fs. Okay. So what do we get now? Then we can write xst, okay, in terms of s and t we want to write. So t z we will put as fs. So fs into t plus s. By is equal to t, and z is equal to fs. Okay. Now using by equal to t, we can write xst equal to fs into y plus s. So we need to solve this. We need to solve this system for the values of s and t in terms of x and y. Okay. We have to write s as xy, sxy, and t as txy. So what do we get? We can write s equal to x minus fs into by r x minus zy. So, we get s is equal to x minus zy and z is equal to fs. So, what do we get? Z equal to fs gives you f of s is equal to x minus by z. So, what we get is the solution of the given initial value problem is then obtained in an implicit form, z is equal to f of x minus by z. So, that is the solution is z equal to fs and s is x minus by z. So, the solution is obtained in the form of a implicit equation. Now, let us consider another problem. Suppose we have the Cauchy linear PDE Zp plus by q equal to x, where the initial condition is given by Zx1 equal to 2x. So, let us write the characteristic system here. The characteristic system is dx by p. P is z, okay, dx by d, let us write like this, dx by dt is equal to p, that is z, dy by dt equal to q, which is y, and then dz by dt equal to x. So, we get the characteristic equations. Dx by dt is equal to px by z, px by z is z, dy by dt equal to qx by z, which is y, dz by dt which is equal to x. And let us parameterize the parametric form of the curve C. Parametric form of the curve C. So, what do you do? What we do? Let us put x equal to s, y equal to 1 and z equal to 2s. Okay. So, if we do this, what we will get then? Let us solve this characteristic system. Solving the characteristic system, we get you see dx by dt equal to z. So, we get d square x by dt square equal to dz by dt, and dz by dt is equal to x. So, we get d square x by dt square is equal to x, and this is nothing but d square minus 1 x equal to 0, where d denotes d over dx. So, solving this second order linear differential equation in x, what we get is the general solution x is equal to, because the auxiliary equation is m square minus 1 equal to 0, which has auxiliary equation is m square minus 1 equal to 0. So, this gives two distinct roots, m equal to plus minus 1, and corresponding to two distinct roots of the auxiliary equation, we have the solutions e to the power t and e to the power minus t of this equation. So, C1s into e to the power t plus C2s into e to the power minus t, we can write for x. This x is xst. Now, what we have at t is equal to 0, we are given x is equal to s. At t is equal to 0, we have x equal to s. So, we have s is equal to C1s plus C2s. Now, we need to find one more condition in order to determine C1 and C2. So, we use the condition that dx by dt is equal to z. So, dx by dt is equal to z, and dx by dt here is what? C1s into e to the power t plus C2s into e to the power minus t. Now, dx by dt is z, that is equal to C1s e to the power t plus C2s e to the power minus t. Put t equal to 0, at t equal to 0, z is equal to 2s. So, 2s is equal to C1s. When we differentiate, we should have got a negative sign here. So, this is negative. Okay. So, minus C2s. Okay. Now, let us solve this equation and this equation for the values of C1 and C2. So, we get C1, when we add them, we get 2 C1s equal to 3s. So, C1s is equal to 3s by 2, and C1s is equal to 3s by 2 means C2s is equal to minus s by 2. Okay. Thus, we have solved this equation dx by d square x by dt square is equal to x, and we got x s t is equal to 3s by 2 e to the power t minus 3s by minus s by 2 e to the power minus t. Okay. Now, we have the second equation dy by dt equal to y. So, dy by dt is equal to y gives you dy by y is equal to dt, which gives ln by is equal to t plus ln let us say C3s. So, what we get, y is equal to C3s times e to the power t. At t equal to 0 we are given y equal to 1. So, 1 is equal to C3s, and hence we get y is equal to e to the power t. Now, let us solve for z. We have dz by dt equal to x. So, let us differentiate once more. We get d square z by dt square is equal to dx by dt, which is equal to z. So, we get again d square minus 1 z equal to 0, which gives you z as t equal to some constant C4s into e to power t plus C5s e to the power minus t. We put t equal to 0, at t equal to 0 z is equal to, we are given z equal to 2s. So, 2s equal to C4s plus C5s. Now, let us so we have got one condition involving C4 and Cs. We need one more condition in C4 and C5 to determine their values. So, we let us find dz by dt. Let us find dz by dt. dz by dt is equal to C4s e to the power t minus C5s e to the power minus t, and dz by dt is equal to x. So, we get at t equal to 0, x is given to be equal to s. So, we get, so s is equal to C4s minus C5s. Okay. Now, let us take this equation and this equation, and then determine the values of C4 and C5. So, C4s, when we add this equation with this, we get C4s is equal to 3s. So, C4s then is equal to 3s by 2, and C5s will then be equal to s by 2, and so z s t will be equal to 3s by 2 e to the power t plus s by 2 e to the power minus t. Okay. So, we have got the values of x s t, y s t, z s t as functions of s and t. Let us now solve them to determine s as a function of x and y, and t also as a function of x and y. So, from this equation, let us see, this is equal to we can write s by 2 times 3 e to the power t minus e to the power minus t. Okay. Now we use this equation by equal to e to power t. So s is equal to s by 2 3 by 3 by 3 by minus 1 over y. Okay, and this gives you what we get 2x. This is 3. Okay, x is equal to 3 y, s by 2, and we get 3y square minus 1 divided by y. Okay, s by 2 3y square minus 1 divided by y. So s is equal to, we can find s in terms of x and y here, 2xy divided by 3y square minus 1. Now what we do, s is equal to here s is equal to s by 2 3 e to the power t plus e to the power minus t. So 3y plus 1 over y. Okay, and this gives you s by 2 3y square plus 1 divided by y. Okay. Now we can write, we can apply, we can use the value of s as 2xy over 3y square minus 1 here and get the value of z in terms of x and y. So z is equal to s by 2, s by 2 is xy divided by 3y square minus 1 into 3y square plus 1 divided by y. So this I can cancel and I get x times 3y square plus 1 divided by 3y square minus 1. Okay. So we have got z equal to x times 3y square plus 1 upon 3y square minus 1, which is an explicit solution of the given Cauchy linear PD. Z is equal to 3y square plus 1 into x over 3y square minus 1. So this is how we solve the Cauchy linear PDE, Zp plus byq equal to x, where the initial condition is given by Zx1 equal to 2x. So with this I would like to end my lecture. Thank you very much for your attention.